Okay, so continuing, in the previous module we looked at the Z transform. In here we're going to continue with the Z transform. We're going to look at the inverse Z transform, and then we're going to look at the different representation of the discrete time system. So the first thing we're going to look at is the inverse Z transform. So there are many methods of finding the inverse Z transform. Now the most popular or the most useful technique for finding the inverse Z transform is using partial fraction expansion. And this is the technique we are going to review here. The most useful technique is partial fraction expansion. For finding the Z transform. And the idea behind the partial fraction expansion is to express the function you want to find the inverse Z transform of h of z as a sum of simple terms that have known Z inverse. So I'm going to take any function and I'm going to try to break it into terms such that these terms I can easily find the inverse Z transform for. So let's look at some examples. So let's say we have h of z equal to z squared plus z squared plus z divided by z squared minus 5 over 6 z plus 1 over 6. So in this case, h of z has two distinct poles. And we can write this x of z. We can find the roots of the denominator. The roots of the denominator, we refer to them as the poles of this h of z. Okay, so if I take the roots of the denominator, if I take z squared minus 5 over 6 multiplied by z plus 1 over 6 equal to 0. First thing, we call this characteristic equation. Characteristic equation. If we take the denominator, we equate it with 0. We call this the characteristic equation. Characteristic equation. Now the roots of this characteristic equation are the poles of h of z. The roots of the characteristic equation are the poles of h of z. So what are the roots of this equation here? I can write this equation as z minus 1 over 2 multiplied by z minus 1 over 3 equal to 0. Therefore, I have two poles, 1/2 and 1 over 3. Okay, so therefore, h of z, I can write it as equal to z squared plus z divided by z minus 1/2 multiplied by z minus 1/3. Now remember, what we're trying to find is we're trying to find h of n. Now what we're going to do is we're going to take this h of z, and what we're going to do is we're going to divide h of z by a z. So before we proceed, let me just continue. Let me copy these so we don't need more pages. Okay, so what we're gonna do, I'm gonna take this h of z and I'm gonna divide it by z. Now this is a tricky step and I'm gonna explain it in a minute. So what I'm gonna do, I'm gonna take h of z and divide it by z. What is h of z divided by z? Since I have z squared in the z squared plus z in the numerator, I can write this as z multiplied by z plus 1 divided by z minus 1/2 multiplied by z minus 1/3. So if I divide by z, I'm just gonna get z plus 1 divided by z minus 1/2 multiplied by z minus 1/3. Now what I'm gonna do is I'm gonna expand this using partial fraction expansion. So what I'm gonna do, I'm gonna write this as c1 divided by z minus 1/2 plus c2 divided by z minus 1/3. What is c1 gonna equal to? I'm gonna multiply both sides by z minus 1/2. So to find c1, I'm gonna multiply both sides. This is z minus 1/2 multiplied by z minus 1/3. I'm gonna multiply, this is equal to c1 over z minus 1/2 plus c2 divided by z minus 1/3. What I'm gonna do, I'm gonna multiply both sides by z minus 1/2, z minus 1/2, z minus 1/2. If I do that, this is going to cancel with this is going to cancel with this, and therefore what I'm going to get is z plus 1 divided by z minus 1/3 equal to c1 plus c2 multiplied by z minus 1/2 divided by z minus 1/3. Now what I'm going to do, I'm going to substitute for z with both sides, z equal to 1/2. So when z is equal to 1/2, I'm going to get 1/2 plus 1 divided by 1/2 minus 1 over 3, and this is going to equal to c1. And if I substitute 1/2 in this term, z minus 1/2 is going to become 0. So therefore c1 is just going to equal to the expression I have on the left, and therefore c1 is going to equal to 3/2 divided by 3/6 minus 2/6, which is going to be a 3/2 divided by 1/6. And therefore this is going to give me a 9. 3 times 6 is 18/2 is going to give me a 9. We're going to do the same thing for c2. And therefore if I do follow the same thing, we're going to see that c2 is going to equal to z minus 1/3 multiplied by z plus 1 divided by z minus 1/2 when z is equal to 1. Well, the z minus 1/3 is going to cancel. So we're going to do the same thing. Z minus 1/3 multiplied by z plus 1, z minus 1/2 multiplied by z minus 1/3. This is going to equal to c1, already we know it's 9 over z minus 1/2 multiplied by z minus 1/3 plus c2 z minus 1/3 multiplied by z minus 1/3. Z minus 1/3, z minus 1/3 is going to cancel, z minus 1/3, z minus 1, sorry, z minus 1/3 is gonna cancel here. And when I substitute with z equal to 1/3, this term, the whole term is gonna cancel. So therefore, I'm gonna end up with C2 equal to z plus 1 divided by z minus 1/2, and I'm gonna substitute when z is equal to 1/3. And therefore, this is gonna equal to, let me just write it here, C2 is gonna equal to 1 plus 1/3 is gonna equal to 4/3 divided by 1/3 minus 1/2. 1/3 is 2/6 minus 1/2, which is a 3/6, and this is gonna give me a negative 8. Okay, so therefore, putting this together, I expanded h of z divided by z as equal to 9 divided by z minus 1/2 minus 8 divided by z minus 1/3. But what I want to find the inverse of is h of z, not h of z over z. Well, then let's take h of z. What is h of z going to equal to? I can multiply both sides by z. I'm going to get 9 multiplied by z divided by z minus 1/2 minus 8 multiplied by z divided by z minus 1/3. And I got my expansion of h of z. Now what I want to find is I want to find h of n. I'm gonna look at this term. I can easily realize this is equal to 9 multiplied by 1/2 to the power k, or h of k, sorry. H of k is 9 multiplied 1/2 to the power k minus 8 multiplied by 1/3 to the power k. Is that clear? Now what we've done is we've taken h of z, we divided by z, and then we multiplied again by z. So we did not change anything. Now the reason we've done what we've done is that when I expand h of z, I would like to see a z in the numerator. And the only way to guarantee that I have a z in the numerator is if I divide by z and then multiply it again by z. Now why do I need that? Because if I were to look at the tables of the z transforms, the tables of the z transform, they will have, it will be easier to use the tables if I have the expansion in this form. And I can immediately look at the z transform table and realize z over z minus a is just equal to a to the k, and therefore z over z minus 1/2 is just going to be 1/2 to the k. Similarly, z over z minus 1/3, 1/3 to the k. And again, this is just multiplied by a constant. It's a linear operation. Okay, so this is how we get the inverse z transform if I have simple roots that are not repeated. Now let's see what happens if I have roots that are repeated. So let's look at another example. So I'm going to find the inverse z transform of h of z equal to z squared divided by z squared minus z plus 1/4. What we can do, we can take this z squared, we can write the denominator as z minus 1/2 multiplied by z minus 1/2. So this transfer function has two poles, but both of these two poles are at 1/2. Now when I want to expand this, I'm going to do the same thing. I'm going to take h of z, I'm going to divide by z. This is going to equal to z divided by z minus 1/2 multiplied by z minus 1/2. How do we expand h of z when I have two poles at the same location? The way we expand this is going to equal to c1 over z minus 1/2 plus c2 over z minus 1/2 squared. This is how we expand repeated poles. One term to the power of 1 and the second to the second power. Okay. What is C2? Now in this, when we expand it like this, C2 is straightforward. C2 is straightforward. I multiply both sides by z minus 1/2 squared, and therefore, and then I substitute by z equal to 1/2. So if I take this and I copy it and paste it here, it doesn't want me to copy paste. Okay. So if I take z over z minus 1/2 multiplied by z minus 1/2 equal to c1 over z minus 1/2 plus c2 over z minus 1/2 squared, what I'm going to do, I'm going to multiply both sides by z minus 1/2 squared. Z minus 1/2 squared with z minus 1/2 squared is going to cancel, and z minus 1/2 squared is going to cancel with this, and then I'm going to substitute when z is equal to 1/2. Now z minus 1/2 is going to cancel with this one, but I'm going to still have a c1 multiplied by z minus 1/2, because the square, one of the terms, is going to cancel with z minus 1/2. This is plus c2 is going to equal to z if I do this multiplication. Now what I'm going to do, I'm going to substitute z equal to 1/2. If I substitute z equal to 1/2, z minus 1/2 is going to cancel, and z is here is going to equal to 1/2, and this is going to equal to c2. So therefore c2 is going to equal to 1/2. Okay. So therefore we found the value of c2. How do we find the value of c1? So let's go back. H of z is equal to c1, h of z over z is equal to z over z minus 1/2 multiplied by z minus 1/2, and this is equal to c1 divided by z minus 1/2 plus 1/2 divided by z minus 1/2 squared. Now what you want to find is the value of c1, and to find the value of c1 we multiply both sides by z minus 1/2 squared. So multiply both sides by z minus 1/2 squared. If I do that, I'm going to get only z on the left side, and I'm going to get c1 multiplied by z minus 1/2. The square is going to cancel with z minus 1/2, and z minus 1/2 squared is going to cancel with z minus 1/2 squared. This is plus 1/2. So then what I can do is I can take the derivative. If I derive both sides, this derivative is going to give me a 1. c1 multiplied by z, if I take the derivative by dz, is going to give me a c1. So therefore c1 is just equal to a 1. Of course, there are other methods. If you can substitute, since here we have only one unknown, which is C1. I can plug in any value for Z and then solve for C1. Or you can always multiply by Z minus 1/2, take the derivative of both sides with respect to Z. So therefore, I have C1 and I have C2. I can write H of Z as C1, which is a 1, divided by Z minus 1/2. And now since I'm writing H of Z, I multiply it back by Z, plus 1/2 multiplied by Z divided by Z minus 1/2 squared. And therefore I can go to the tables, and this is going to tell me H of n is equal to 1/2 to the power of k plus k multiplied by 1/2 to the power of k. Okay, so this is finding the inverse of Z transform when we have repeated roots or poles. Okay, so let's look at the next representation. Now that we reviewed the Z transform, we're going to look at the all delay block diagram. Again, we're going to be using the Z transform throughout, just like we were using the Laplace transform in linear control. We're going to be using the Z transform in this course. So please review it, refresh on it. Again, we'll have the homework to help you come up to speed with it. If you need any help, let me know. Of course, read the book. If you need more help, let me know. If you want to watch some lectures that reviews the Z transform, also let me know. Okay, so in the continuous time systems, we looked at all integrator block diagram. Now, what we're going to look at for the discrete time systems is the all delay block diagram. So in addition to the difference equation and transfer function, so we looked at difference equation, we looked at transfer function, and another representation that we will introduce is the all delay block diagram. All delay block diagram. Okay. Now, in order to introduce the all delay block diagram, let's look at the ideal time delay element. An ideal time delay element is represented as following. We have a delay. This is a T. This is a delay element, has an input and it has an output. It has initial condition E of 0, and it has an input E of k plus 1, and it has an output E of k. Every t seconds, a number is shifted into the time delay element, and at that instance, the number that was stored in the element is shifted out. So every t seconds, a number is shifted into the element, and at that instance at that instant the number that was stored in the element is shifted out. So let's see, when k is equal 0, when k is equal 1, when k is equal 2. So in this case, when k is equal 0, E1 is stored in the element. E1 is stored, and E of 0 is shifted out. At k equal to 1, E of 2 is stored, and E of 1 is shifted out. At k equal to 2, E of 3 is stored, and E of 2 is shifted out. Okay, so this is what the delay elements. We have a register that we input to it an input, and on the clock we also output the current whatever value is on that register. So let's see how we can use this time delay element in order to construct the all delay block diagram for a discrete time system. So we're going to construct all delay block diagram for a linear discrete time system. And this system is described by the following equation. Described by a difference equation, that is y of k plus 2 plus a1 multiplied by y of k plus 1 plus a0 y of k equal to b0 multiplied by u of k. Okay, first thing we're going to do is we're going to construct a chain of time delay elements with input as y of k plus n and output that is y of k. So in this case we have y of k plus 2, so I'm going to take y of k plus 2 as an input. This is y of k plus 2. If I input it to a delay element, I'm gonna get y, let's write it here, y of k plus 1. If I input it to another delay element, I'm gonna get y of k. Y of k, the initial condition is gonna be y of 0, y of k plus 1, initial condition is going to be y of 1. Okay, so this is generated a chain of time delay elements with input that is y of k plus n and output that is y of k. Okay, so then we're going to use this equation here in order to complete the diagram. I have y of k plus 2. What is y of k plus 2 equal to? Y of k plus 2 is equal to negative a1 y of k plus 1 minus a0 y of k plus b0 multiplied by u of k. So therefore I can come here, so this y of k plus 2 is equal to b0 multiplied by u of k. So this is u of k multiplied by b0 and then I have minus a1 multiplied by y of k plus 1. So I'm going to take a1 and negative sign, and then I have minus a0 multiplied by y of k. So I'm going to take a0 and feed it back to get y of k plus 2. And this will give me the all delay block diagram. Now notice here, and hopefully by now, since we've seen it in the homework, in this case this system does not have any zeros. So if I were to write the transfer function for this system, there are no zeros in this transfer function. So let's look at another example where we have zeros in the transfer function. So let's look at example 2. And in this example, we're going to have a system that has finite zeros. So the system is y of k plus 2 plus a1 multiplied by y of k plus 1 plus a0 multiplied by y of k equal to b1 u of k plus 1 plus b0 u of k. Notice here I'm going to have zeros for this system, and we have initial conditions y of 0 and y of 1. Okay. How did I know it's y of 0, y of 1? Because when I start the calculation, when k is equal to 0, I'm going to calculate y of 2. And y of 2, I'm going to need y of 1, and I'm going to need y of 0 to calculate it. So y of 0 and y of 1. Okay. So let's calculate the transfer function. So transfer function, and to calculate the transfer function, remember we set the initial conditions to 0. And if I calculate take the z transform, I'm going to get z squared y of z plus a1 multiplied by z multiplied by y of z plus a0 equal to b1 multiplied by z multiplied by u of z plus b0 multiplied by u of z. The transfer function is y of z divided by u of z. Okay, what is this equal to? This is going to equal to b1 multiplied by z plus b0 divided by z squared plus a1 multiplied by z plus a0. Notice here I have, as this transfer function has a 0. The example before did not have a 0. This transfer function has a finite 0, which is equal to negative b0 divided by b1. Finite 0. The 0 location is minus b0 divided by b1. How do we find the all block diagram representation? We use similar trick that we've done with the all integrator block diagram. I'm going to take y of z over u of z, and I'm going to write it as e of z divided by u of z multiplied by y of z divided by u of z. oh, this is E of Z, sorry, E of Z over U of Z multiplied by Y of Z over E of Z. Again, these cancel each other. I'm going to get back U of Z over Y of Z over U of Z. Okay, but then what I'm going to do, I'm going to divide the transfer function that I have here into two parts. I'm going to take Y of Z over U of Z, and I'm going to say this is equal to 1 over Z squared plus A1 multiplied by Z plus A0 multiplied by B1 Z plus B0. This part is going to be equal to this part, and this part is going to equal to this part. And again, the division is not random. E over U, we're going to use it with the denominator. Y over E, we're going to use it with the numerator. Okay, so if I do that, then I'm going to have E of Z over U of Z equal to 1 over Z squared plus A1Z plus A0. And therefore I can multiply across. This is going to be Z squared multiplied by E plus A1 multiplied by Z multiplied by E plus A0 multiplied by E equal to U of Z. I can take the inverse. This is going to be E of K plus 2 plus A1 E of K plus 1 plus A0 multiplied by E of K equal to U of K. Therefore, I can write E of K plus 2 as equal negative A1 multiplied E of K plus 1 minus A0 E of K plus U of K. So what we're going to do, similar to what we've done in the previous example, we're going to take E of K plus 2. We're going to delay it. We're going to delay it. This is going to give me E of K. This is delay. This is E of K plus 1. This is E of K plus 2. This is E of 0. This is E of 1. And this E of K plus 2 is going to equal to the input U of K, and is going to equal minus A1 multiplied by E of K plus 1. So this is A1, this is positive, this is negative, and then minus A0 and then multiplied by E of K. Okay. Are we done? No, because we calculate plug diagram to E of K, but what we want to calculate to the output. So therefore, we're going to come to Y of Z over E of Z, the second part, which is B1 multiplied by Z plus B0. We can multiply across. This is going to give me Y of Z equal to B1 multiplied by Z multiplied by E of Z plus B0 multiplied by E of Z. And therefore, Y of K is equal to B1 multiplied by E of K plus 1 plus B0 multiplied by E of K. Now, I can go back, and what I'm going to do, I'm going to just shift this down, and I'm going to go back to diagram so we don't have to repeat it. So what I can do, I can come here and say, okay, the output y of k is equal to b1 multiplied by e of k plus 1. So I can take e of k plus 1, multiply it by b1, and then take e of k and multiply it by b0. Now I can do it either way. I can take it from here and multiply it by b0, and then if I add these together, what is that going to give me? It's going to give me y of k, and these are both added together. Now again, the way I plot this, it doesn't matter. I could have done the same thing, I could have taken this from here and had b0 and then add them together and add them here. That doesn't matter. Again, okay. But I'm saying the layout does not matter. I could have had the adder up here or here, doesn't matter. What matters is the connection are correct. Okay, so this is my all delay block diagram. Now this is very important because this is going to help us determine the next representation of the system, which is the state space models. So I'm going to stop here. The next module, we're going to look at the state space representation, and we're going to be using the all delay block diagram in order to get this representation.